All right, it's 5:30, so let's go ahead and get started today. So good evening, everyone. How's everyone doing on this fine Wednesday evening? It's week 2 of the semester. Good? Great. Yeah, good to see everyone's doing well so far this semester. Okay, so today we're going to be covering something new. So we're going to be covering what's called the stiffness method. So it's kind of a way to implement the finite element method, and I think it's kind of a nice way to kind of illustrate just kind of the broader concept within finite element. So we'll see kind of what that means when we dive into the lecture. But before we get started with that, I want to clarify one thing for the homework. So I got some questions on the homework about, how you guys should show your results, because there's a lot of questions that are like, what's the maximum stress? What's the maximum displacement? So for those kind of questions, what I want you to do is, you should tell me the numerical value of what you obtained from your simulations. But I also want you to show me a screenshot of your ANSYS profile as well. So for any question that asks, show me your ANSYS results, you should answer the question, but you should also give me a screenshot of the color contours as well. So like when you run your simulation on your plate and you get like your stress distribution or your deformation distribution, take a screenshot as well, and then include that in your PDF for the to get full credit. Okay. Okay. Are there any questions on the ANSYS activity or just anything about the class that I can answer before we get started for today? All right, so the question is, what about the MATLAB questions? So for the MATLAB questions, you can either write out your solution by hand and submit that, or you can type it out, or you can just send me a screenshot of your solution from MATLAB as well. Yeah, so you don't have to show the code working, because I know what the correct code looks like. So just sending me the code that you wrote either by screenshot or by writing it down, that works for me. Okay, so let's go ahead and get started today. So the topic for today is the stiffness method for finite elements. Okay. And so, what this stiffness method is it's a way to kind of implement the finite element method. So, this class is kind of like a little bit of a misnomer. It's like it talks about the finite element method and the finite element analysis. So finite elements is kind of just like a general term for like a whole class of methods that kind of treat, these physical problems in a certain way. So there's not one singular finite element method. The finite elements is kind of like a broad umbrella, and there's kind of lots of different ways you can implement the finite element method. So the stiffness method is one way to implement the finite element method. And it's, I chose to start with this in the class because it's fairly simple. And I think it really kind of highlights a lot of the big features of, different finite element implementations. But if you ask me, if the stiffness method is used in practice, it's not actually used that much for practical situations. So if you look under the code in ANSYS, you're not going to find anything, at least, not specifically in terms of the details of what we're going to cover today. But, the reason we're kind of starting with this is that it's just a nice, really good introduction to, what finite elements is and how do we set up a problem and how do we think about problems in kind of a finite element context. Okay, so our starting point here is, we're going to start with hopefully something that's familiar to everyone, which is Hooke's law. Okay. And so Hooke's law is a way that we can characterize the behavior of a spring. Okay, so let's go ahead and draw a spring. Okay, so let's say that we have a spring and it's attached to the wall. So this wall here is fixed. Okay. And so the spring has its spring constant K. It might have had an original length L. Okay. And then due to some force that's pulling on it, so let's say that we're pulling on it with the force F, the spring has displaced by an amount D. Okay. And so what Hooke's law says is that the relationship in between the force and the displacement is given by the following equation. Okay. So hopefully this jogs some memories back from, maybe a previous physics class or a previous, structural mechanics class, right? And so what Hooke law says is that if you have some kind of applied force, okay, so we have an applied force F, so we're taking the spring and we're pulling on it, so that's something that we're applying. Then as a result of that applied force, the spring is going to deform, so this D right here is the displacement of the spring. Okay. And then the relationship between, how much the spring is going to displace relative to the force is given by this proportionality constant K, where K right here is our spring constant. Okay. And so kind of the upshot from this, or what I really want to focus on, is that spring constant K. Okay. So K here is going to determine how our spring responds to an external applied force F. Okay. Another thing to note is that this spring constant K is a property of the spring itself. So it's like a material constant for the spring. Okay. And so that might be, maybe an interpretation of Hooke's law that you might not have seen before, but it's going to help us with, how we motivate these finite element problems. Okay. All right. Are there any questions on just Hooke's law right here before we move forward? Okay. Okay. So that's a single degree of freedom system. So we have one side of the spring that's fixed, and we're pulling on that side. So we have one displacement and one force. Okay? So let's generalize this. So let's generalize this to a system where both sides of the spring are free. And the way that we often describe this within finite elements or any kind of computational science is that we now have 2 degrees of freedom. Okay, so let me draw my spring, our spring again. Okay. Okay. And let's say that the left side of the spring is given by, we'll number that with node 1, and then the right side of the spring will be node 2. Okay. So instead of having a single force and a single displacement, we can now say that at the left-hand side, we have an applied force, but we also have a corresponding displacement. Okay. And on the right-hand side, we have the same thing. So we have now, instead of just a single displacement that we're solving for, we now have 2. So we have a 2 degree of freedom system. Okay. So it's you don't have to just stop here. So you can keep generalizing. So you can have a system with dozens or hundreds or thousands of degrees of freedom, or different displacements that you might be interested in solving for. And that's generally what finite element problems tend to be, is that you have hundreds or thousands of different degrees of freedom that you want to solve. Okay. And so in these cases where you have more than 1 degree of freedom, you can't just have a scalar expression like F is equal to KB, right? Because, this doesn't take into account all the different forces and all the different, displacements that you might find. So we need to generalize our kind of our force displacement relationship. Okay. And so our system should now look something like this. Okay. So it looks, all the letters are the same, but I've added some additional symbols here. Okay? And so let's define everything here. Okay? So where, for our one-dimensional Hooke's law, we had just an input force, but now, we're generalizing this. So now we have, many, many forces. So instead of a single force, what we have is a force vector. Okay. And then same thing for the displacement. So instead of having a single displacement, we now have a vector of displacements because, we have one for every single degree of freedom. So this is our displacement vector. Okay. And then instead of a single spring constant, what we have here is in order to kind of make the math work between these two vectors, what we have instead is what's called the stiffness matrix. And so the stiffness matrix is going to play, even though it's a matrix instead of a number, it's going to play the same role as our spring constant, as in it's going to relate the applied forces to all the displacements that result from that. Okay. Any questions on this?
Excuse me, Professor, I have a question.
Sure, what's up?
So I thought like degree of freedom, they have to be like in different directions to be like considered as a degree of freedom. And then like when we like define a vector, so it's like in X direction and in Y direction, but both of these displacements are in X direction, as I can see in the image.
Yep. Yeah, no, that's I think that's one way to define degrees of freedom. So, in kind of a classical sense, like I think degrees of freedom refer to, the different coordinate directions. But in this case, I use the term degree of freedom to talk about how many unknowns that we're solving for in our system, right? And so in this case, we have two unknowns. So we have, displacement 1 and displacement 2. And so I use the term degree of freedom to refer to both of that. So I think you're right in that degree of freedom is kind of used differently in different contexts. But for finite elements, when I say degree of freedom, I mean the unknowns in our system, or how many things that we're solving for. Yeah.
Got it. Thank you.
Mm-hmm. Okay. Okay. So that's kind of the idea with the stiffness matrix, is that it relates kind of the input forces to the displacements that result from that for any system. So for now we've shown just like a spring with 2 degrees of freedom, but this concept can be applied to much bigger systems. Okay. But actually in reality, the idea of a stiffness matrix can be generalized even more, right? And so in this class, we're going to be talking a lot about, structural mechanics problems. So the term actual stiffness actually, has some physical meaning there. But you can use finite elements for all different kinds of problems too. So the other one I think we'll be covering a lot in this class is heat transfer. But you can also use finite elements to solve fluid mechanics or even electromagnetics as well. Okay? And so the stiffness matrix and actually the forcing vector and the displacement vector, they kind of have more general definitions. So just as kind of an aside, I kind of want to go and talk about this a little bit. Okay? So let's write out our equation again. So we have F is equal to K underscore. Right? So I use an underline. So the notation I'm using here is anytime I have something that's underlined, that refers to a matrix. Okay, so let's generalize these definitions such that we can use the same kind of format and the same kind of terminology for all different kinds of problems like heat transfer, fluid mechanics, whatever. Okay, so let's start here on the left. So we have F here. So before that, F represents some external forces that we're applying. But if we generalize this to like heat transfer and stuff like that, this F right here represents any kind of external loading effects or any kind of external forcing that's happening on your system. So some example for this, you know, for structural mechanics, this could be, you know, external forces themselves. Right? And so if you're talking about like heat transfer, this could be like heat fluxes. Okay. Or just more generally, you know, if you want to talk about just general problems, anytime you have boundary conditions, then that appears here. So there's a question in the chat. They're asking about body forces. So body forces would be included here as well. But if you think of body force as something like gravity, I kind of consider that to be kind of like an external effect. So, you know, a body by itself doesn't generate an external force. Like if you know, shot yourself into space, you know, you wouldn't generate a force. But the fact that we have a gravitational body force comes from the fact of, you know, the external forces from the Earth. So body forces would be included in that vector too. And so the general term for our displacement vector here would be the solution vector. Okay? So this is oftentimes what we're interested in solving for in a finite element context. So, you know, for structural mechanics, this would be like displacement. Okay? So we're solving for the displacements that result from, you know, our external loads or external forces. But this could also be things like temperature for heat transfer. Or velocity, like if we're solving fluid mechanics. And then finally, we come to the stiffness matrix here, right? And so the stiffness matrix, you know, the way that we generalize this is, you know, this is a stiffness matrix of material properties or properties of the system. Okay? So these would be kind of like intrinsic properties of the physical system that that would go in here. Okay. So some examples of this would be like material constants. So things like density or like the Young's modulus, you know, that would factor into the stiffness matrix. All the effects of the geometry would be in here as well. So basically, any property that's you know, that's intrinsic to the system that, you know, behaves kind of the same way, kind of no matter where you are, those usually go in the stiffness matrix. Okay? And so one thing that you can test is, you know, you can say if you take your object like your pen and then you chuck it into space, right? Would the pen still have like the same mass? Would it still have the same geometry, right? So all those things that are kind of intrinsic to the object itself, that goes into the stiffness matrix. Right? So I know I'm talking about this in kind of very broad terms, but, you know, this system right here, even though it looks very simple, you know, all kinds of finite element problems kind of fall within this system. So heat transfer, fluid mechanics, electromagnetism, structural mechanics, of course, they fall into the system where you have a vector of external effects, a solution vector that you're looking for, and then a matrix that has all of your intrinsic material properties and geometry for your physical system. Okay? So everything kind of falls into here. So I wanted to kind of take a moment just to kind of talk about this because, you know, once we start doing like heat transfer problems, you know, we're still going to use the same format. So this kind of format of like having a stiffness matrix, it's not unique to just structural mechanics. Okay, are there any questions on this? Okay, so now that we kind of understand, the purpose of the stiffness matrix and what it represents, let's actually derive what that is for a spring. Okay. And so the contents of your stiffness matrix will depend on the physics of the situation and the the actual properties of your material. So the spring is kind of like the simplest thing that we can do. So that's why I kind of want to start here. Okay? And so let me draw our spring again. Okay. So we have two nodes. We have a force on the left-hand side, a force on the right-hand side, and then we also have displacements. Okay. And so, if we want to write this in matrix form, we write our forcing vector. So our forcing vector here is just going to be a 2 by 1 because there's only two forces. Right? Okay. And our solution vector here also has only two elements. We just have D1 and D2. And so in order for this system to work, our stiffness matrix needs to be a 2 by 2 matrix. Okay. So I'm going to leave it just in general for now. So you can say that we're interested in solving for for the stiffness matrix. So that means solving for all four of these constants. And the reason I knew it was a 2 by 2 matrix is because our forcing vector is 2 by 1 and our solution vector is 2 by 1. So in order to have basically this to work, or at least the linear algebra to work, this needs to be a 2 by 2, right? Because with a 2 by 2, you cancel out these internal ones and you multiply a 2 by 2 matrix by a 2 by 1 vector and you get a 2 by 1 vector from it. Okay. And so what we're going to do is we're going to solve for what all of these constants need to be in order to satisfy this thing for a spring. Okay. Okay. So before we do that, let's make an assumption just to simplify things. And so let's assume our spring is in equilibrium. Okay, so our spring is not moving. Okay? So if we sum up all the forces on the spring, then they equal to 0. Okay? And so that means F1 and F2 have to be the same magnitude, but just opposite in direction. Okay? And so if we redraw our spring, okay, so in order for the spring to be in equilibrium, we need to have a force in, on the left. So we'll say that that force has a magnitude of T going to the left. And then on the right-hand side, we have another force T, so equal in magnitude, but opposite in direction. And then that's holding the spring in place. Okay? And so from this, we have just by intuition, we know that if we tug on the spring to the left, on the left-hand side of the spring, then we're going to have a displacement going towards that left. And then on the right-hand side, since we have a force going to the right, our displacement that way is also going to the right. Okay? And then throughout this entire thing, it would be good just to specify the positive x direction. So if we define the positive x direction going to the right, that means these guys right here are going to be going in the negative x direction. And so we're going to use the fact that our spring is in equilibrium, and we're going to use the directions of the system to solve for the element stiffness matrix. Okay. All right, any questions on this? Okay. Okay, so now that we have our system kind of defined in that way, let's start to actually apply some equations. And so let's first apply Hooke's law. So remember, Hooke's law relates the applied force on a spring with the total displacements. And so, since in this case we have a force of T pulling on the spring essentially, then what we have is T is equal to K times delta. Okay? Where delta right here, delta is the total deformation of the spring. So some of you might be asking, why isn't this 2t? Because we have a t on both sides. But what we're saying basically is the spring is in tension with the force of t. So that's why we only have one t in this equation. It's not 2t. Okay. So that's the Hooke's law. So Hooke's law says that the applied force T is equal to K times the total deformation. Okay. So we can simplify this a bit, or maybe not simplify this, but put this in terms of variables that we know. So let's express delta, or total deformation, in terms of the nodal displacements. Okay. And so our nodal displacements are D1 and D2. Okay. And so if we go back to this figure right here, we can see that we have the spring is displacing to the right D2, and it's displacing to the left of D1. Okay. And so the one expression that we can get for the total deformation is we can just add up these two displacements. And so we can say that delta is equal to D2 minus D1. Okay. So notice that I used a minus D1 there because D1 is going to the left, so it's going to be negative. Okay. And so we plug that back into the expression up there, then what we get is T is equal to K D2 minus D1. Okay. So that's how we can relate the tensile force T to the nodal displacements D2 and D1. Right. Okay. So now that we have this expression, we have a big part of our stiffness matrix here. Okay. So we have basically this side. Okay. But in order to complete the system, one way that we can do that is we can have equations for F1 and F2. Okay. So let's put T in terms of F1 and F2. Okay. Okay. And so if we do that, remember F1 is the force that's applied on the left-hand side of the spring, so on the left node. So so the way that we could do this, and we can relate this back to our figure, is we can say that F1 is equal to minus T, okay? And then F2 is equal to T. Okay? Because remember, F1 is pointing to the left, so it has to be a minus tension, right? And then F2 is pointing to the right, so then we have a positive tension on that. Okay? Any questions on this before I turn the page? Okay. And so if we plug in the, for those expressions, so first we have F1 is equal to minus T, right? So if we plug in our formula for T, what we get is F1 is equal to minus K times D2 minus D1. Okay. So all I did was I plugged in for T there. Right. And then similarly, we can do F2 is equal to T, which is equal to K times D2 minus D1. Okay. And so now that we have these equations where we relate, the force that's on the left-hand node to the displacements, and then we have an equation that relates the force on the right-hand node and related that to the displacements, we're ready to put this in matrix form. And then once we put this in matrix form, we'll have our element stiffness matrix from here. Okay? So let's go ahead and do that. So let's go ahead and express the first one. Okay? Actually, I just said we need to put this in matrix form. So let's go ahead and do that. Right. So in matrix form, on the left-hand side, we have F1 and F2. Right? And then for this guy, we need to express this in terms of D1 and D2. Right? And so we're basically just taking our system of two equations and two unknowns, and we're putting in matrix form. So this is just like what we reviewed last week. Right? And so if we do that, we get the following coefficients. And so the coefficient for D1 on equation 1 is going to be a positive K, right? So we have a minus K multiplied by a minus D1, so that's going to be a positive K. Right? And then the coefficient for D2 on equation 1 is going to be minus K, because we have minus K times a positive D2. Okay? Next, we have the coefficient for D1 on equation 2. So the coefficient for D1 is a positive K multiplied by a minus D1. So that's going to be a minus K. Right? And then the coefficient for D2 is going to be a positive K multiplied by a positive D2. So that's a positive K. Okay? Right? And so from this, we're able to extract here our element stiffness matrix. And so our element stiffness matrix for a spring is simply K, minus K, minus K, and K. Okay. Where little k in this case, remember, this is our spring constant. Okay. So it's very simple. So as long as you know the spring constant for a spring, you can just plug it into this formula right here, where you have a symmetric matrix with a positive K on the diagonal, and then a minus K on the off diagonal. Okay. Any questions on how we got this element stiffness matrix for the spring?
I have a question, Professor.
Sure. What's up?
So for the first line on this page, F1 equals negative T equals negative K, D2 minus D1.
Yeah. Mm-hmm.
So I don't know why you just put negative K there instead of K.
Right. So remember, our formula for T was from this page, right? So T is equal to K times D2 minus D1.
Yes.
And so since F1 is equal to a minus T, and so this minus right here came and I just put that minus right here on that guy, right?
To make it like T equals K D2 minus D1.
No, so so this minus sign just came from the fact that F1 is equal to minus T, right? And so if you look at the our original figure here, so since T right here is going to the left on node 1, and so what we say is that the force on node 1 is a minus T, because it has a magnitude of T, but it's going to the left. So that's why we put that minus sign there. And so that minus sign here comes into this right here. So all I did when between this side and this side was I just plugged in for T, because we knew that T has this expression right here, right? And so when we plug that in, then this minus sign is still there. So then this minus sign just comes out on this side of the equation right there.
Got it. To cancel out the minuses, so get to the t equals k d2 minus d1.
Yes. Yes.
Okay.
Yeah.
Okay.
That's one way. That's one way to look at it. Yep.
Got it. Thanks.
All right. Any more questions on this? Right. So the question from the chat is, can I explain why we have d2 minus d1 instead of d2 plus d1? Definitely, I can do that. Right? So it's the same motivation as to why f1 is minus t. And so because we know that we're pulling to the left on t, then we know that d1 has to also go to the left, right? And so since d1 goes to the left, then we know it has to have a minus sign. So that's why we have d2 minus d1, okay? Because remember, this delta right here is a measure of the total deformation, right? And so in order to get a measure of the total deformation, you need to get d2, which is positive, minus d1, which is negative.
Sorry, I just need to ask another question.
Sure. Yeah, what's up?
So for this, like, I was thinking, like, if I want to, like, write the total deformation, I would write, like, instead of delta, d2 plus d1. And then instead of the force, I would, like, put in 2t equals k d2 plus d1. But then it doesn't help us get the matrix, right? Because I thought, like, that 2t force is causing the d2 plus d1 deformation, kind of like that.
Yeah. So, I mean, the reason, we only do a single t in this case is because, we're considering it just on the nodal basis. So we're saying that this node right here, this node number two is expressed is getting a force of t, right? And so that's why we have it just a single t right there. And then the total deformation here, in order to get that, this is a total deformation of the entire spring. So remember, in Hooke's law, this total deformation is defined as the change in length of the spring, right? And so one way that we can get the change in length from the nodal displacements is to do d2 minus d1. Does that kind of make a bit more sense?
To be honest, not really, but I have to think about it. Yeah.
Okay. Yeah. Maybe we can talk in office hours or offline, and then a bit more. Yeah.
Sure. Thanks.
Yeah. It is weird because we have a t in each direction, but the spring itself is only experiencing a force of t. So if you think back to kind of your physics classes, if you have like a string, right, and you pull on that, and the string experiences a tension of t. So even though if you pull a force of t in this side and a t in this side, the tension in the string is not going to be 2t, it's just going to be 1t, right?
1t. Got it. Thanks.
Yeah. So think of like the spring that's attached to a wall, right? So if you have a spring that's attached to the wall and you pull it with the force t, the other side actually has a force t in that direction too, because that's the normal force that's from the wall. And in that case, you still say that the spring itself is experiencing just a tension force of t. Yeah. Yeah, it is a bit confusing, I think, especially if you haven't seen this kind of stuff in a while. But once we have that, then we have this element stiffness matrix that's given in this form. So the current config isn't 2 times distance from the reference or the origin. Right. So I mean, we're measuring the distance of each node kind of relative to its original position. Yeah, that's why it's only just a single d2 and a single d1. Right. So the question from the chat. So even though the f1 and f2 are different, the t is the same at both nodes. That's correct. Yeah. Yeah. So so normally f2 and f1 can be different, but we're considering just a single spring here, and we're assuming that the spring is in equilibrium. So the t's have to be the same. But from that, we kind of backtracked and set that equal to f1 and f2, which gave us the equations that we needed for this element stiffness matrix here. Yep. Okay. So that's the element stiffness matrix for the spring, but that's for a single spring. But in reality, when you have a finite element system, a lot of times you have, multiple elements. Okay? And so the next thing we're going to go over, which is kind of be a review from last week, is how do we assemble a system with multiple elements. And so let's take kind of a simple case where we just have two springs in series with each other. Let's say that we have a fixed wall over here, and we have one spring, and they're attached, and then we have another spring. Okay? And then let's say that we're pulling on this entire assembly with the force F. Okay? So let's say our first spring has a spring constant K1, our second spring has a constant K2, right? And then we'll label all the nodes. And so let's say that we have node 1, node 2, and node 3. Okay? And then just like before, each of these nodes can be displaced. Right? So each of the displacements of the nodes are given by D1, D2, and D3. Okay? So here we have a two-element system, right? And then what we want to do is we want to solve for, the displacements D1, D2, and D3. Okay? And so the first step in doing that is we can write out the element stiffness matrices for each of these springs. So we have two springs in this case, right? So we have spring 1. Okay, and so that's our element stiffness system for spring 1. Okay, and then we also have the same thing for spring 2. Okay, and so for spring 2, it also has its element system. Okay, so one thing I want to highlight to you guys, before we move forward, is that for spring 1, you'll notice that the displacement vector that I gave you is D1 and D2. Okay, but in comparison, the element stiffness system for spring number 2 is D2 and D3. Okay, and so the reason for that is that, the way I pick these numbers is that these numbers represent the nodes that these elements are touching. Okay, so in element one right here, you can see is touching nodes 1 and nodes 2, right? And so that's why in the element stiffness system we have D1 and D2, right? Meanwhile, spring number 2 is touching node number 2 and node number 3. Okay, so that's why we have D2 and D3 for this guy. Okay, and so this is really important because the next step for this is we're going to take these element stiffness systems and then assemble them into one bigger system. So you want to make sure that you get these node numbers and these node indices correct, so that you can put them in the correct spots in the global system. Okay. Okay, and so the global system, will just be one linear system that captures this whole thing. We'll have will be a 3x3 system. Okay. Right. And so I drew the column labels just to kind of help us out with that. Okay. So we have F1, F2, F3 is equal to our 3x3 global stiffness matrix, and then that's multiplied by D1, D2, and D3. Okay. Okay. So then now let's start to go through the process of adding the elemental contributions. And so we have two element stiffness matrices here. So we have the element stiffness matrix from element 1, and then we also have the element stiffness matrix from element 2. Okay. So let's start adding these guys in. Okay. And so what I've done right here is I've taken the element stiffness matrix from element 1, and I've put that into the global system, right? And so the reason I chose this location for here is because element stiffness 1 acts on D1 and D2. And so we put all these guys into the D1 and D2 slots into the global system. Okay. And so next, let's do element 2. And then just to kind of highlight this, I'm going to use a red. Okay. Okay. And so inputting element 2 into the system will give us this, this expression right here. Okay? So I box the location for element 2, and remember element 2 is corresponding to D2 and D3, right? So I put all of these K2s into the D2 and D3 slots into the global system. Okay. And so this step is necessary because, you know, when you have a multiple element system like this, you know, ultimately what you want to solve is just one linear system that covers the entire assembly. And so putting all the individual contributions into one global system is really important for this. Okay. All right. Any questions on assembly? All right. So the question is, if D2 is to the right, wouldn't the element stiffness matrix change for K2? So you're saying if we swapped nodes 2 and node 3? Oh, if D2, wait, can you I'm not quite sure what you're asking. Ah, okay. Yes. So so you're saying if D2 instead, because in the previous example we had the left node going to the left and then the right node going to the right, right? So in the previous one it was kind of like this, right? So we had D2 or D3 minus D2. Yeah. So in this case, you know, we you know, it wouldn't change it because right now all the D's are kind of expressed within with the respect to the positive x-axis, right? So one thing that I didn't draw here was the positive x direction was pointing this way. Right? So we can always assume that the positive x direction is always going to the right. So in this case, you know, we assumed, you know, the way I drew this, you know, I'm drawing all the D's to be positive in that direction. And so that's kind of just the standard that we do. And so in the previous example, you know, we had the left node going to the left, just because, you know, we knew the force on that was going to the left as well, and that's why it was negative. But you know, that same element stiffness matrix can still be applied here, even though the forces are going into the different directions, just because the positive x-axis is defined in exactly the same way. So even though I've drawn it here where all the D's are going to the right, you know, we can still use the same element stiffness matrix because our positive x-axis is defined in exactly the same way. Yeah. Yeah, I know I know all the conventions and all the signs and everything is a little bit confusing, but you know, once we put it all together and solve a problem, hopefully it makes a bit more sense. Yeah. All right, any more questions on assembly?
Okay. Sorry, I have a question.
Sure, what's up?
The other places we have just placed a 0, that's right?
Yes, yeah, so any place that doesn't have anything is a 0. Mm-hmm.
Thank you.
Mm-hmm. Okay, so we need to do one more step before we actually solve, and that's applying boundary conditions. And so boundary conditions, you know, these represent basically all the external effects that are being applied to our system. Okay. So in this example here, we have two external effects. And so on node 1, we can see that node 1 is attached to a wall. And so node 1 is fixed. So that's kind of a constraint that we apply. So that's the same as, you know, when we did our ANSYS example, you know, we had the plate fixed on one side. And so that's one type of boundary condition that we'll do. And then we have another external effect here on the right where we're pulling with a certain force. And so that's kind of be the same thing as, like, you know, the pressure that we were applying on our ANSYS plate. Okay. So these two types of boundary conditions, they have different names. Okay. So I'm going to throw a bit more terminology at you guys, but it's you know, it's important. Okay. And so the first type of boundary condition, and this matches up with the node that's fixed at the wall. And so these are known as Dirichlet boundary conditions. Whoa. Okay. And so Dirichlet, you know, it's a very fancy name, but what it refers to is our boundary conditions where we directly specify the solution value. Okay. And so, a common example of this that you'll see in practice a lot in ANSYS is constraints. Right? Okay, so like in this example, we have a fixed constraint. Okay. All right, so there's a question in the chat. So is it harder to compute a solution for a fixture BC on an edge than on a surface if you're in 2D, 3D? I think that's a question that I'll probably take offline. But yeah, let's talk after the class about that. Yeah. So in this particular case, in this particular example, an example of a Dirichlet boundary condition would be the node that we have on the left-hand side. Okay, and so since this node 1 is fixed to the wall, we can say for sure just from the beginning of this problem that displacement d1 is going to be 0 because it's attached to a wall that's not moving. Okay, and so since we're directly specifying the value of that displacement, then that is a Dirichlet boundary condition. Okay. And so the other category of boundary conditions that we'll go over is known as Neumann boundary conditions. Okay. And so Neumann boundary conditions, they're comprised of external forcing effects. Okay. External forcing effects that do not directly specify the solution value. Okay. So in this particular case, we have an external force, right? So we're pulling with the force F, right? And so in this case, when you pull with the force F, that's an external effect that's going to affect our system, but it's not directly specifying the displacement. So, just because we're pulling with the force F there, we don't know, at least off the top of our heads, what this D3 is going to be, right? Because the behavior of D3 is going to depend on how the springs respond to that force, okay? So in this case, our force here is an example of a Neumann boundary condition. Okay. Okay, and then and so what's going to happen with these boundary conditions and how we apply them is that these are going to affect our our matrix set of equations that we have for our system. Okay. And so the way that we modify our system according to either Dirichlet boundary conditions or Neumann will be a little bit different, and that's what we're going to do on the next page. Okay. All right. Are there any questions on this before I move on? Okay, so let's see, you know, how do we apply our boundary conditions? Okay. So first, let's look at our Dirichlet boundary conditions. Okay. So remember, Dirichlet boundary conditions, we're directly specifying the solution variable. And so in this case, our solution variable is the displacement. And so what we're basically going to be doing is we're going to, you know, replace an entire row in our matrix with that boundary condition. Okay. And so let's look at our system again, or let me just draw part of it. Okay. So this is just part of our two-element system from before. Okay. And so what you can see here is that node 1 is completely fixed. Okay. So since node 1 is fixed, okay, the way we express this mathematically is we can say that D1 is equal to 0. Okay. Right. And so what this gives us is this actually gives us an equation, D1 is equal to 0, that we can actually apply into the global linear system. Okay. Okay. So I'm going to write, you know, this very simple equation, D1 is equal to 0, in a very strange way. And you know, it's going to seem really strange at first, but you know, it's going to help us modify our system. Okay. So another way to express D1 is equal to 0 is like this. Okay. And so if we have this matrix system right here, where we have a vector of 1, 0, 0, and then we multiply that by a column vector of D1, D2, D3, okay? And you actually perform the matrix multiplication here, you know, what you get is the same thing. So you get D1 is equal to 0, okay? And so the reason I wrote it like this is that, you know, in this form, this allows us to basically replace an entire row in the matrix with this expression. Okay. Okay. So let's go ahead and do that. Okay. So let me redraw our entire 3x3 system. Okay. And then let me draw the other two rows. Okay. And so I've drawn our, you know, our global system, which was, you know, this guy right here, right? So I've redrawn that entire thing except for the first row, okay? And so before in the first row, we had things like KA, minus KA, and 0, okay? But since we have a Dirichlet boundary condition on that first node right there, what I'm going to do instead is replace the row in the matrix with this, okay? So we're going to do 1, 0, 0, okay? And then on the other side, we're going to have 0, okay? And so if you perform the matrix multiplication for this first row, and then you would see that you would get this exact equation right here, D1 is equal to 0, okay? And so for Dirichlet boundary conditions, the way that you apply them is that you replace an entire row in the matrix with that Dirichlet boundary condition, okay? Right, any questions on how we apply Dirichlet boundary conditions? Okay. And so, you know, the row that you pick is really important too, because notice that, you know, for D1, I pick the row where D1 is in the diagonal slot here, okay? And so for D1, you want to pick the first row in the matrix. But if we had a situation where, you know, D3 was equal to 0, in that case, we would pick the last row in the matrix because that's the row that corresponds to D3. Okay, and so that was Dirichlet. So thankfully, Dirichlet boundary conditions are, you know, the more difficult of the two to apply. And so let's do Neumann boundary conditions now. Okay. And so to apply Neumann boundary conditions, you know, the way that we apply them is we just modify the forcing vector. Okay. So very simple. So we basically just take the value of the Neumann boundary condition and then just plug that into the forcing vector. Okay. And so let me redraw our system here. Okay. Right. So there's our linear system. Okay. And so I want to draw your attention to the forcing vector that's over here. Okay. And so the forcing vector, remember what these represent. So F2 and F3, these represent the forces that are applied on those nodes. Okay. Okay. So F2 is the external force that's applied on node 2, and then F3 is the external force that's applied on node 3. Okay. And so in this particular case, we do have an external force that's applied on node 3, right? And that is going to be the force F, right? So remember if I draw this element again, right? We had an external force of capital F on node 3, okay? And so to apply that boundary condition, we just replace F3 with, you know, big F, which is our boundary condition. Okay. And in this particular case, since we don't have an external force that's being applied on node 2, we can just set F2 equal to 0. Okay. Right. And then now that we've done all that, you know, we have our global linear system, and then we can just, in order to solve this, you know, you can solve this by hand if you're a masochist. But you know, most people when they solve these systems, they see, you know, a big scaling linear system. You can either plug this into your calculator, or what I like to do is I like to plug this into MATLAB to solve. Okay. And so remember, the goal for this for these kinds of systems is to solve for whatever's in the solution vector. Okay. And so we're solving for these guys. So, you know, when you plug this linear system into MATLAB, what you're going to do is you're going to create a vector, and then input all the values from the forcing vector on the left-hand side, right? And then you're going to create a matrix, and then you're going to input all the values from our matrix here, and then you're going to invert the matrix in order to solve for D1, D2, and D3. Okay. All right. Any questions on this before we do an example? It's a long process, I know, but you know, hopefully once we do an example, it should all come together. Okay, so let's do an example. So in this example, let me draw the geometry first. So we have a wall on one side. Okay, so we have a spring. This spring is connected to a block, okay, which is connected to two more springs. Okay. Let's give all these guys values. Okay. And so we have three springs here. So the first spring is has a spring constant Ka. The second spring has a spring constant Kb, and the third spring has a spring constant of Kc. Okay. Let's label all the nodes. Okay. And so we have four nodes in this system. So we have node 1 that's attached to the wall. We have node 2, which corresponds to the block. So node 2 might look a little bit strange because we have three springs connected to it. But since they're connected all to a solid block, that block is going to move all together. So we're going to count everything that's connected to the second, everything that's connected to the block. We'll call that node 2. We have node 3, which is hanging out over here, and then we have node 4. Right? And so on node 3, we're going to apply a force to the right, and it's going to have a magnitude of F3. Okay? And then on node 4, we're going to apply a force to the left, and we'll call that F4. Okay? And so this block right here is rigid. Let's put some values into this guy. So let's say that Ka has a value of 500 newtons per meter. Okay. Kb has a value of 100 newtons per meter. Okay. Kc has a value of 250 newtons per meter. Okay. F3 will be 100 newtons. And then F4 will be 50 newtons. Okay. Okay. And so from this problem, we're interested in solving for all the nodal displacements. So we're interested in solving for the displacement of node 1, node 2, node 3, and node 4. Okay. Any questions on the setup for the example? Okay. Okay. So the first step in these problems is to write out the finite or the element stiffness matrices for all the elements. Okay. So I'll start it on this side, and then I'll continue it on the next page. Okay. So let's do element A first, right? So that's Ka. So Ka is connected to nodes 1 and 2, and it has a spring constant of Ka. Next, we have element B, or Kb, and Kb is connected to nodes 2 and 3. Okay, so we have F2, F3, and that's equal to Kb minus Kb minus Kb, Kb. Okay, and this is D2, D3. Okay, and then we have one more element here, and that's element C, and then we'll write that on the next page. Okay. Are there any questions on how I got these element stiffness matrices for elements A and B? Okay. And so we have one more element. So we have a 3-element system. So that's going to be Kc. And so element C, element C is connected to the rigid block, so it's going to be connected on F2 on the left-hand side, and then on the right-hand side is going to be connected to node 4. So that's why we have F2 and F4. So we have to be careful when we add this one because it's not going to be in one contiguous block. So we're going to have to place this kind of carefully. But we'll cover that. We'll cross that bridge when we get there. Okay, so we have KC minus KC minus KC, KC, and then that's going to be D2 and D4. Okay. Okay, and so once you have all the element stiffness matrices for all the elements, the next step is to assemble them all into the global system. And so our global system in this case will be a 4x4 since we have 4 nodes. Okay, so let's go ahead and write that out. So we have F1, F2, F3, F4. Okay. Okay. So we have D1, D2, D3, D4, D1, D2, D3, D4. Okay. And so let's take each of the element stiffness matrices and add them to our global system. Okay. And so first, let's start with element A. So element A is connected to D1 and D2. Okay. So I'm going to write that in red in here. So we have Ka minus Ka minus Ka, and then Ka. Okay. Right, so that's element A. Okay. Next, we're going to do element B. So element B is connected to node 2 and node 3. Right, so we have Kb minus Kb minus Kb, and then Kb. Okay. So that's element B. Okay. And then finally, we have element C, which is given by this guy right here. Okay. And so you can see here that this is connected to the D2 and D4 nodes. Okay. And so the places that we're going to add it, I'm going to go ahead and box, right? Okay. And so since this is, 2 nodes that are not next to each other in the matrix, we have to make sure that we add them all to the appropriate D2 and D4 slots. Okay. So the first slot is going to be right here. So I kind of ran out of room, but imagine that there's a plus Kc there. And so in that D2, D2 slot, we have Ka plus Kb plus Kc. Okay. And then we write in all the other guys just like that. Okay. All right. Any questions on how we assemble this matrix? Right. So now that we have our global matrix, the next step that we're going to do is we're going to apply boundary conditions. Okay. And so we have 3 boundary conditions here. So we have one boundary condition on the left, which is D1 is equal to 0. Okay. Okay. And so D1 is equal to 0. That's going to be a Dirichlet boundary condition. So we're going to replace the entire first row. Our next 2 boundary conditions are Neumann. So then we're just going to move those into the forcing vector. Okay. So we have little f3 is equal to big F3, and little f4 is equal to big F4. Okay. And so when we come back, so Monday's a holiday, so we're going to come back next Wednesday. And so next Wednesday, I'll show you. We'll kind of finish up this example and see how these guys plug in. Okay. But that's all we got time for today. So thank you everyone for tuning in. I haven't made the minute paper for this week, but I'm going to make it in just a second, so it should be up in 5 minutes. Okay. But if not, you guys are free to go. So thank you guys for tuning in again. Have a great long weekend. So remember, Monday's a holiday, so don't show up on Monday. I won't be here. Okay, and then I'll see you guys on Wednesday. Okay.
Professor, but the homework is due by Monday, right?
Yeah, the homework is still due on Monday, so it will be due by 11:59 on Monday.
Okay.
All right, so there's a question in the chat. So for the homework, would you like to send a screenshot of our results in Microsoft Word? Yeah, so you don't have to send me your ANSYS files, but whenever I ask you for like a certain result in ANSYS, like the maximum stress or the maximum displacement, I want you guys to take a screenshot of that and then put that into your Microsoft Word document. Yep. All right, Chris, are you still here? You're still here. Okay, so regarding your question from earlier, if you're in 2D or 3D, if you're applying a fixed boundary condition, it's actually the same. So you just follow the same procedure, you just replace the row in the matrix. And so, your matrix is going to be a lot bigger in 2D and 3D, but the process is still the same. So if you have a Dirichlet boundary condition, it's basically the same amount of difficulty. It's just you're working with a really, really big matrix.
Quick question, Professor. Can you hear me?
Yep. Mm-hmm.
So for number 1 and 2, since that's the ANSYS, that's the ANSYS portion, you only want us to do, you just want everything in Microsoft Word, you don't care about the files or anything, right?
Yes, yeah. So just send me your results. So you don't have to send me your ANSYS files or MATLAB files or anything like that. So just put it all into a single PDF and then give me that.
So just screenshot it. Okay.
Yeah, just screenshot and then put that into your Microsoft Word and then send me that.
Okay. No, I just want to make sure. Thank you.
Mm-hmm.
Professor, one question.
Sure. What's up?
About this example. So for is the F4 the one that you draw the picture? Is it the F4 is to the right or to the left? The force.
So F3 is to the right, and then F4 is to the left.
So can we just put the small F4 equals to negative large F4?
Yes. Actually, yeah, that's a good point. So actually, this should be a minus F4 because I gave you F4 in terms of magnitude, which is 50 newtons right here. And so so on next Wednesday when we plug it in, this would be a minus 50 right here.
Got it. Great.
Right, because it's to the left. Yeah, good catch. Mm-hmm. Yeah, so you can do the save image to clipboard and mechanical, or you can just take a Windows screenshot. So either one works for me. I'm not going to be a strict stickler for the image quality, but either one works. Yeah. All right, so there's one more question in the chat. So can I explain why D1 is equal to 0? Yeah, definitely. So D1 right here represents the displacement of node 1, okay? So if we go back to our diagram right here, node 1 is, attached to this wall right here, okay? And so since that node 1 is fixed to that wall, then we know that node 1 or D1 is going to be 0 because there's no way for that node to move because it's basically bolted to that wall. And so no matter what we do on the rest of the system over here, it doesn't matter because node 1 is going to be fixed to that wall. And it needs to be fixed to that wall. Otherwise, we have a system that's going to be moving in space. So we want to have at least one anchor point where we know the displacement is 0. Yeah. Right. Are there any more questions?
Another question, Professor.
Sure. Yeah. What's up?
So these are only for the external forces, right? We cannot do these calculations with internal forces, right?
Yeah. So there will be internal forces that develop from this, but those don't make it into the system because we only factor in things that can basically affect change in the system. So you can have internal forces that that develop as a result of this. But for the finite element system, we're only interested in things that can cause like a displacement, and that's that's only going to come from external forces. Yeah. So we'll see. Not next week, but the week after that, we'll see. How we can actually compute those internal forces, and we're going to see how we do that for these kinds of systems.
That's what I wanted to know. I can cut a beam and then just draw the internal force and then calculate, make it define it in a different global system, kind of like that, right?
Yeah. So we'll see, you know, how we take, you know, a finite element solution like this and use that to compute like internal stresses or internal forces. Because a lot of times, you know, that's why you do a finite element solution to begin with, is because you're interested in, you know, those things that are normally really hard to compute. But for finite elements, it's very easy to do those kind of things. So yeah, we'll see that in a couple weeks.
Great, thanks.
Professor.
Yep.
So for problem 2 and 3, where you say like show the ANSYS color contours, is that the same thing as just taking the screenshot of the ANSYS project?
Yeah. So the color contours would be things like the equivalent stress distribution or the total deformation. And so when I say show me the color contours, just take a screenshot of, you know, of the ANSYS interface, which shows that. Yeah.
Okay.
Last question. Are there office hours tomorrow?
There are office hours tomorrow. So office hours tomorrow will be from 4 to 5:30. Yeah.
Great. Thank you. Have a good day. Bye.
Thanks, you too. Bye. Yep. Thanks, guys. Have a good weekend, everybody.
Thank you.
All right. Any last questions, Fernando? I know tomorrow we have we'll discuss the you know, what you emailed me about, but I think, yeah, tomorrow might be a better place because I think we'll have more time to discuss that. Okay, so I'm going to end the call here, and then, you know, I guess I'll see you guys next time.